So again, I'll just welcome you to the AMATYC webinar series. We've got Jason Martin here today to talk about guided reinvention of series convergence and Taylor series convergence, which should be a great webinar. I saw the first part of this webinar a while ago. In the AMATYC Association, one of the core values is to help instructors enhance their personal growth, and so these webinars are all about that, and providing year-round professional development. As expressed by presenters are not necessarily the views of AMATYC, and any commercial products that I mentioned are not endorsed by AMATYC. The webinars are provided by the Lift Institute at Muskegon Community College, and if you have suggestions about future programs, please feel free to contact me at maria.anderson@muskegoncc.edu. And we will now shift it over to Jason. So I'm going to stop sharing this screen and let Jason go ahead and share his screen, and I'm going to stop sharing my webcam and mic. So take it away, Jason.
Okay, well, thank you very much, and you should be seeing the screen now. So on my end, as I'm sitting here noticing, on my end, I see just the PowerPoint slides. And so I'm not going to see some of the other stuff, other features. So when there is a poll question, I'll try to back away and let's see that. I did notice that in the earlier announcements for this, I apparently had some superpowers that I could spin the world backwards and make time go in a different direction. So that I thought that was pretty awesome. So Maria, do you want me to go ahead and start at this point? Should we wait another minute or so? Is everybody able to hear me okay? Or did I lose people?
Yeah, we can hear you okay. You can go ahead and get started, but whatever you just did took the slide away.
Yes, okay. I see it now. Okay. Yeah, I have difficult.
Yeah, so I'm going to keep my mic on so I can let you know if there's a question.
I was just making sure, and yeah, the chat window goes away when I'm sharing, so that's.
There we go.
Okay. And when I go to look, yeah. Okay, we'll get it going then. And Maria, you can just interrupt when needed. So I want to begin with just a quick little poll question. And so on your end, a poll should be popping up of some of the topics in calculus which do you think your students perceive as being the most difficult. And Maria, on the polls, does it actually say what A, B, C, and D, what these are?
Oops, I don't know what I did to the poll. One sec. Poll.
And I'm going to pull away while so I can see the results.
There we go. Now it's back up on the screen.
Okay, so I think that's everybody. So my multivariable. Yeah, so my experience usually when I'm talking with students about this, which do you think is the most difficult? That usually sequences and series and power series are at the top of the list. Sometimes I say vector, sometimes multivariable calculus, but a lot of times they have a tendency to put this sequences and series, power series up high, and when they do multivariable calculus, when they're talking about limits and differentiation, for many students, it can come across as easier because in some respects it's a repeat of some of the things that they had done in Calc 1 and Calc 2. So my perception is that most students, a big chunk of them, see this series thing, and I group sequences and series together. I thought about splitting them up, but the series thing, whether it be series or power series, is something that is they perceive as being something that's very difficult. After looking at these students struggle with some problems, I love this quote in the subsequent title of their paper: "Do students really get it?" And so today I want to kind of reveal some of the things that they do get. So another quick poll question. This is actually a continuation of another talk, the reinvention of sequence convergence. And I was just kind of curious about who here had previously seen that. I'm going to pull away momentarily so I can see the poll. So Yeah. So if you haven't seen it, I'm still going to revisit some of the results from that, because this is a talk that's really following the same two students. There's two students that we called Megan and Belinda. And we're going to follow those two students prior or following their experience in creating their own sequence convergence definition. But we're going to follow them in this talk to series and point-wise convergence in the context of Taylor series convergence. So the outline today, we're going to have some research overviews, goals, talk a little bit about layers of abstraction, the study. And then I will talk about the other talk, and then series and power series.
Yeah, just type in the chat window if you have a question, and I'll type it up to
just let Maria
Jason
know, and then she'll get my attention, and I'm pretty laid back, and we'll just kind of go through this together, and I'll try to answer anything that you have. So we wanted to detail how students come to understand formal limit definitions. And we really thought that there was pretty good literature on about how students understand some limit definitions, but this idea of how they come to understand formal limit definitions, how they move from some sort of informal reasoning to a more formal type of reasoning, that literature on that was hadn't very well filled that area in. In doing so, we wanted to know what challenges do students face when creating a limit definition. And we really saw these challenges as opportunities for learning. How do the resolutions, so if the students engage a challenge and they struggle with it and then they resolve this challenge, how does it support them in creating their own definitions, their own sequence convergence, their own series convergence, their own point-wise convergence, or as far as they're going to think, some definition for Taylor series convergence. And what is the instructor's role in helping students effectively engage in these challenges during this creation of these definitions? To help us better see students struggling through this process, we decided to be, I like to think of this as guides on the side. We wanted to design these instructional activities, and I have A, B, and C here kind of listed, and you can read them, but I kind of think of A as we wanted to meet students where they're at. We wanted to leverage the knowledge that they already knew. They were not blank slates. They had informal ways of reasoning about limits. And we wanted to formalize and systematize their understanding. And in C, in a sense, we wanted to take ownership of we wanted the students to take ownership of their ideas instead of us sitting there lecturing them and them getting ideas from the book or getting ideas from an instructor. We wanted them to take ownership of their ideas, and that in the end, when they have these definitions written down, that they see that as their definition. And so that when they see it in the textbook, they're not seeing the textbook's definition. They're really seeing their definition in the textbook. We feel like this would be something that would help it be a much more meaningful experience for the students. I want to introduce something that wasn't necessarily talked about in the first talk, and this is the idea of layers of abstraction. And you see these little bitty boxes here down at the bottom of the screen, and those boxes represents different problems in a context. So a group of 3 boxes could be different problems in derivative, and a group of another 3 boxes could be different problems in integrals, and different problems in series and Taylor series. And so in the course, the students had to reason about these types of things and do different applications and reflect upon the common structures and actions involving sequences. So they had multiple application problems with sequences, and then they had to kind of think about and reflect on what they were doing and what makes a sequence a sequence. And the same with series, and then the same with power series. And the goal then was, within each of these little boxes, is when we're doing power series, for example, they're having to coordinate graphical, numerical, and formulaic reasoning, and in doing some sort of one application problem. And there are questions that are being asked, and all of these things they're having to coordinate as they're doing these problems in calculus, whether it's like a Taylor polynomial is approximating sine of x, and they're having to talk about that and graph a picture and give some numerical values of like what sine of 1 is, and how does this polynomial approximate sine of 1, and if we increase the degree, how does that, so they can have a better understanding of some of the underlying structure of Taylor polynomials and Taylor series. And then the overall goal, they can look at all of these, whether it be derivative, integral, sequences, series, that they can see some commonalities among them that helpfully support the formalization of the mathematics. So that was the course that the students came from. But we pulled these students, and that layer of abstraction idea is present in just about any course in calculus, but there was an intentional emphasis on that in this particular course. So we pulled students from that course to this teaching experiment. It was a 6-day teaching experiment. We're going to be focusing mainly on day 4 and day 5. These were calculus students that had sequences series and Taylor series experience, and so at this particular university, that means it's a second semester calculus class. Each session was 90 to 120 minutes in length, and for series and Taylor series, it was the 120 minutes in length. So over these 6 days, they initially had to create their own sequence convergence definition. And the goal was then to move them to a formal series convergence definition where they're creating their own, and then move them to pointwise convergence. So the first talk that was given by Mike Ortman and Craig Swinyard focused on sequence convergence definition. And this talk will focus on the two. So of the first 5 days, what happened was we thought in day 1 that they were very close to a sequence convergence definition, and we left the teaching experiment giving each other high fives because we thought they were so close that within about 20 minutes tops on day 2, they would have a really nice sequence convergence definition that they saw as their own definition. We were wrong. They weren't as close as we thought they were. But after day 2, the angels sing, and we have a really nice definition. And these students who had no prior experiences with the formal definition. So one key thing is this formal definition was not something that was presented in their calculus class. So they had no experience with this formal definition, created a sequence convergence definition that looked like something you'd see in a textbook. They went from something very informal to something really nice. Then on day 4, we do series convergence, and on day 5, we do pointwise in the context of a Taylor series. In particular, it was a Taylor series for e to the x, so it had an infinite interval of convergence. So I think it's worth reminding people that have seen the previous talk what happened with sequence convergence. And if you hadn't seen it, to give you an idea of this is what these students had already experienced before going into series and Taylor series convergence definitions. So in this, we had the students engage in an iterative refinement process. We had a board covered with examples of sequences converging to 5 and examples of sequences not converging to 5. So their goal was really to capture all those sequences, write a definition that captures all those sequences converging to 5 and excludes all those sequences not converging to 5. And what we found was that students entered this refinement process where they would articulate a definition. But in doing so, there might be some sort of problem, and they would identify this problem with this definition. And usually that identification occurred as they were evaluating their definition against all those examples and non-examples already on the board. They would acknowledge and discuss any conflict between their definition and their concept image, or these pictures up here on the board, discuss potential solutions, and then take another stab at it, write another definition. So here's my next poll. How many iterations do you think these students did before they produce their final definition, a definition that, like I said, looked pretty much like a definition in a textbook. So I'm going to pull away here to see the poll results. Okay, so we got 5, 15. Okay, so I'm going to pull back now. Okay, you should see the presentation again. Okay, so here we go. They have this prompt: a sequence convergence to 5 as n goes to infinity provided. So as you can see, nobody, at least nobody got it. So in even 23 is not the answer. These definitions actually represent complete and utter restarts of their definition. For example, there might be a 23A, B, and C where they write 23 and they make a quick change, and then they make another quick change, and they make another quick change. So the number of iterations is actually much more than 23. So these students were very persistent in going through this process. Another thing to give you a picture of what all was going on is given by this pretty busy graph. And in this graph, you'll notice this word problem. You'll notice this word problematic. You should notice this word solution. So I want to highlight a few things. So very early on, the students had a problem. They wrote their definition. And the definition they wrote was: a sequence converges to 5 as n goes to infinity, provided that the number approaches or is 5 and no other number. So this is their second definition. It involves some pretty common words, dynamic words. And then what happens is, what if the graph just does anything at the beginning? And then it kind of converges. So they felt like this definition too had a problem in that it very explicitly expressed by the student. There are a lot of other issues with this definition, but this problem that they saw was this idea of bad early behavior. And very quickly, they had a solution, this idea of at some point. And that moved them to definition 3. As n goes to infinity, at some n, this a sub n plus 1 becomes closer to or is. So they incorporated this at some n into their definition because they had addressed this problem of bad early behavior. But there are other issues going on. Some issues that the students had not seen yet, and we refer to those as problematic issues. So there's several problematics that stem from this idea of at some n. For example, there's uses of n in multiple ways here. They're not being clear about which a sub n's they're referring to. If you look down at the bottom, n is actually tied to convergent behavior. That after this random stuff, here's where it starts to converge. Here's where the behavior starts. And this n, and likewise, this n is fixed. But instead of addressing these problematic issues, thereby turning them into problems, they saw another problem, and that is how close is close. So while they're addressing how close is close, they come up with this idea of acceptable range. So that was explicitly addressed. And then that's actually an implicit solution to n is tied to convergent behavior. Now what happened? That n was tied to the acceptable range. But the thing is, there was only one acceptable range, and n was fixed. So that almost reinforced the other problematic issue of n being fixed. But then later on, another problematic issue that actually occurred pretty quickly was what epsilon allows non-limits. And so eventually, after they had wrestled with this problem for quite some time, the yellow here kind of indicates the facilitator is kind of stepping in after they had articulated many ideas consistent with this for every epsilon, but just hadn't quite put it there. The facilitators kind of stepped in and said, well, what if you have this for every? And they latched onto it really quickly. And once they'd latched onto it, the idea for every epsilon was something in their definition and something in their definition that remained stable. You saw it repeat and repeat and repeat and repeat. So what I really wanted you to see is that the students had already engaged in this type of definitions.
Do you think that the fact that remained a stable part of their definitions from that point on was because it was suggested by the facilitator, or because they?
I think it's because.
Okay.
If they had not been wrestling with the problem, there were things that in this one epsilon to for every epsilon, that they had wrestled with that for, I believe, around 1 hour. And they had articulated all the ideas behind the solution, but they just
The
put them all
wrestling
together.
is pretty
and
important,
all we did
I
is say, oh, well, does this capture this idea that you've already been talking about?
Okay.
Had they not been wrestling with them, I don't think it would have taken. This idea of engaging in problems and wrestling with the problem, it prepares them. They either get the solution on their own, it's great, or if they wrestle with it, prepares them in a way to be ready to hear the solution. So all this type of language. 2 days later, definition 23, something looks out of the textbook. Okay, so now we go to the invention of these definitions. Again, I think it's important, along the same lines of the question that Maria asked, that these challenges are opportunities for learning. This engagement of problems is opportunities for students to learn. So we want to see what challenges they engage and how they resolve these. But there's also something else going on here. They've already done a lot of stuff with creating a definition. So we want to see how their prior experiences in the previous day also influence their experience. This first example of a sequence, convergent sequence, looks like here they have it to 0, came out pretty readily. But then they actually say stuff to me, and they started focusing on formulas and generating some formulas. And the facilitators eventually said, we need to steer this ship to more productive waters. And in doing that, what we decided to do was, let's not focus on a formula. Just start producing some pretty readily produce a few more graphs. So here's another example. They are realizing that and indicating that they have. So they did, in doing this, they had some informal descriptions. No prompt yet had been given to produce a series convergence definition. But by the end of day 3, a few informal descriptions had occurred. And that's when, some of the descriptions kind of been read. You see this kind of dynamic language, pretty typical type language for limit. You got going to, closer and closer, smaller and smaller and smaller and smaller. But they're also making distinctions between what partial sums are and what the terms are. So that's actually in front of them. And the prompt is, a series converges epsilon n convergence definition.
Just my mouse fell off of it and it didn't come.
So I'm going to pull away while the poll is being put up.
Hey guys, I'm afraid that we may have lost Jason here for a second. I noticed he stopped talking and then the my Adobe platform froze and now he's not here. So hopefully he'll think to come back into the room. I need to send him a little email here. So just bear with us for a second. I'm guessing his screen froze at the same time mine did. Are you all still here? Can you put like a yes in the chat window so I know I've still got some people here? Okay, good. That's probably him calling. Hey, Jason. Did you get kicked out? Oh. Hold on a second. Jean, I'm in the middle of a webinar. Can I call you back? Okay, bye. The mystery continues. Where is Jason? Let's see. I'm going to jump in the slides to where Jason was so that when we get him back, he can get started right away. I think we should be about here. Unfortunately, I don't have Jason's phone number. Let me double check. Maybe I've got it somewhere. Found his phone number. I'm calling him. Hey, Jason. Uh-oh. So he's still talking. He doesn't realize he's lost us. One sec. Hi, Jenny. Can you go down to Jason Martin's office and tell him that this is Maria Anderson? Thank you. All right, we should get Jason back momentarily here. he seems to have gotten cut off, but I think his Adobe Connect is frozen, so he doesn't realize he's gotten cut off. So if you just bear with us a sec, I will get him right back. This is a first, actually. We've had some other weird things happen, but never this. We found out where Nell was from. Where are you from, Mike and Wilbur? We'll have a little small talk while we wait for Jason to get back here. Ah, there's Jason. He's back. We had like something of a freeze, and then all of a sudden, when I came back in, you were gone, and couldn't figure out why you weren't coming back. And then I realized your computer must be frozen. So I pulled up the slide for where we last saw you, and it might be easiest if you can just start right on this slide, so that we can just kind of pick up where you left off. But make sure your audio is on, because I can't hear you yet.
Okay, can you hear me? Hello? Hear me? Okay, so everybody's able to hear me. I got one person saying yes. Anyone else hear me?
Oh, I can hear you now. Yay.
Okay.
So sorry, you're going to feel a little bit like deja vu, because I think you've already said this stuff, but this is where we were when we last saw you.
So, okay. Give me a second here. Okay,
You just had the poll, and after that we lost you.
Yeah, so hopefully the poll surprised you a little bit, in that they're able to recreate this in 2 minutes. And one of the reasons we feel like they're able to recreate this is because they immediately identified things as graphically being very similar to sequences. And then making this recognition, even though they saw differences. They saw differences between the sequences and series graphs, but they saw these graphs as being very similar. Another thing was the language that they used. They had, when talking about sequences, they had used approximation length, talking about the little dots being approximations to the limit. And they'd use error bounds. They'd used this type of language before, and you see that language also helping them to organize their emerging series convergence definition. So what we had is, within 2 minutes, they had that really nice definition, and then 1 hour later they had that. And so in the deja vu talk, I spent some time talking about what happened during that hour. In this newly not deja vu talk, I will say they was clear. So we'll start here. After they had written their definition, it was very clear that they understood the role of their new definition on series graphs, the roles of like epsilons and n's, and they were able to coordinate these things nicely. So here we have Blenda. So here's a convergent graph. I see how this one works because we pick any epsilon, move the epsilon, it wouldn't matter for all of them, the end value, partial sums. So that worked really nicely. And then Megan, there's actually a epsilon here that's slightly smaller, and she moves the n and says, okay, well, this works. So they did some really nice applications of this. They actually did it with the harmonic series as well, and demonstrated, well, the n really doesn't exist for the harmonic series. It may look like it's converging to, but if you go out far enough, it gets outside that error bound. If you choose any other number, it also does that as well. And so the n just really doesn't exist for that harmonic series. Okay, so we move to Taylor series. Skip that and go to, we decided instead of asking them a questions, or instead of giving them a prompt to say, what does it mean for a Taylor series to converge, we say same over an interval, as opposed to the same at the center of convergence. They were the same over an interval. Along the graph, actually create that function, actually be that function. It was something very prevalent for them. Polynomial makes a polynomial be that approximated function over some sort of growing interval of exactness. We came along and said, well, let's make sure they look at this particular dot. We highlighted like x equals 1, had them highlight what's going on there at x equals 1. Even after doing that, you can see Craig, one of the facilitators, yeah, so just at x equals 1, you're saying your approximations would equal, in Blenda, basically e. Greg's like, E? Okay. Now, before, when we talked about approximation, we talked about errors. And they're like, yes. So if the approximation equaled E, what would the error be then? And without any sort of hesitation, they're both, well, the error is 0. So there is no error between this polynomial that's centered at 0, but we're talking about at x equals 1. There is no error between the polynomial and e to the x. So they were saying the error would be literally 0. When do you think that would happen? Blend or Megan, based on where we're at right, 3 more terms makes these Taylor polynomials be the same to the function. So there's definitely a problem with the definition. This problematic issues with their concept image effect, and eventually turn this problematic issue into a problem. One of the things we did is to help facilitate this is we went up to the board and had them write a formula for e to the x. And I know it's not showing that very well, but we had them write this convergence formula, or this Taylor series formula for e to the x, which they did, and then we highlighted the tail of the series, and it's x to the 6 over 6 factorial plus dot dot dot, and we're asking, so what's this dot dot dot? What's this stuff at the tail? And very quickly they said, oh, the tail is still technically not really 0, even though it's very small. It's not, that tail part isn't really 0. Like up to here would be a good approximation of what happens. Blend the underlines like the first 5 terms. And up to here, that would be a pretty good approximation. But everything else, the total sum of everything would converge to E. So that you're saying the total sum now of everything, that's what converges to E. So this, he points to, is just approximates. So she points to the first 5 terms, says that just approximates E, not the whole thing. So if I give them the prompt, and yeah, some of that isn't showing up on this screen, but the prompt was this Taylor series, and we had 1 plus x plus more stuff, converges to, there's a Taylor series for e to the x, converges to e to the x provided what? You fill in the dot. And they do something really nice. So, okay, well, we could use similar idea from sequences and series, so they're tying that in. But even though they tied that in, and even though they've now produced a graph where they've highlighted not only values for x equals 1, but x equals like a half, and x equals -1, and so on, they still struggle seeing connections between series and Taylor series graphs. I want to show you a little bit of what that means. So Megan had actually started the definition, but she hadn't gone any further than really writing down the prompt. And they had their series convergence definition in front of them. They had the sequence convergence definition in front of them. And Belinda starts talking. And she says, I don't really see that cap in thing happening. And she actually does a vertical gesture, so you can see her hands kind of held vertical. She does kind of this chopping motion. I don't really see that cap in thing happening. She goes on, the graphs look very different. So the graphs mean series and Taylor, look, these things look very different. If people try to use that in, people aren't going to know what the heck is going on. So if we tried to use that in, they're not going to know what the heck is going on. And then she does something really nice. She turns around to the graph I just shown you. This was a little blurry, but she turns around where x equals like 0.5. She starts highlighting their Taylor series graph. And she says, so if I used an in, like if I said an error bound, and so she has, if I used an in, there's some in, and so where everything afterwards is going to be within that error bound, she comes up and does a little error bound sign. She does that little motion. That's not going to make any sense. It's not going to work at all. And Belinda or Megan even chimes in, it's not going to work. And then she does it again, explaining again how it's not going to work. Here's my in. So here is Belinda's in. Here is Belinda's epsilon. And so I never really appreciated what was happening until after the fact. I think during it, I was in panic going, what in the world is she doing? This isn't even close to what we were wanting them to do. This is not capturing. But she's making very accurate statements. That in and that epsilon are not going to work. So she sees a problem. But there's also a problematic issue. One of the problematic issues being that the focus seems off. They're not necessarily seeing series graphs as a part of Taylor series graphs. So we moved them back to a number line. And so this is a series graph now, but instead of graph in your typical 2-axis version, it's graphed as a 1-axis version. And we see epsilon, S of n's, and they start applying this to a series, looks like here, converging to 5. And they're able to apply their series definition to this graph. We then highlighted what's going on here at A and B, at which point they said, oh, well, these are series graphs, and oh, okay, so epsilon is here and here, and they start unpacking their series definition particular to A and then particular to B. And then they express a need to expand their definition. That also, I should note that they realize that n is different, each of these, that their cap n is different. At which point they expand it. So Taylor series converges to f of x when forever there exists n such that, and what they do, they basically kind of took their series definition and tacked on a for all x at the end. They also incorporate their the idea of, oh, we're converting to a function, so they're using f of x's, but they tack on this for all x at the end, which is not point-wise convergent, actually uniform. So we move them back again to the number line and get them to rearticulate that n is something that is dependent upon x, which they recognize n is dependent upon x, and then they kind of look back at the definition and they felt like their current definition just didn't capture this dependence. Yeah, and so this is some of the, so I'll explain what this should look like. So moving back to the vertical number lines, they came back and removed, so they had this for all x. Go back. So you see this for all x, they felt like this didn't capture that. And so in addressing, well, n is something that's dependent upon x, they never clearly articulated moving the for all x up front. One of them actually said for all. We kind of brought them back to that. And eventually they're struggling with this problem. They've identified the issue that n is dependent on x, and their definition doesn't capture that, but it never really articulated a solution. And finally we kind of came in and said, so what if you move that for all x up front, which is what they did. They moved it up front, and then from that point on, they really felt like it captured that definition. To kind of recapture what I've been talking about, they had problems with sequences, series, and power series. And in moving to creating their series definition, they were able to reflect on their prior experiences in creating their sequences definition. And so even though they reflected on the similarities and differences in graphs of sequences and series, and they saw structural differences, they also recognized graphical similarities and recognized that they can apply elements from their sequence definition to their emerging series definition. And then likewise, they're able to recognize graphical attributes in creating their power series structure. So I'll let you kind of think about 6 months later, what do you think happened? So 6 months later, we sat down with them and we asked them, what do you think? So this was a poll. Oh yeah, there it is. And we're almost done here. So after this, it's got a couple more slides. So what happened was A is not the answer, and neither is E. What they recalled were phrases from their definition, like the such that or the epsilon thing, and they recalled certain phrases, but the extent to which these things had been connected had broken down a little bit. What I also thought was interesting is they recalled problems, and they recalled some graphs. There are certain iconic graphs, like the vertical number line. There are certain iconic graphs with sequences that was presented earlier, that once they recalled these graphs were attached to problems that they had previously resolved, and all of a sudden they moved really fast in recreating their definition. So it wasn't as nice as we would have liked. We would have liked them to remember the entirety of their definition, quickly correcting omissions, but that's not exactly what happened. But what did happen was pretty good. They remembered these phrases, and then they remembered problems, and as they were kind of recreating it again, when they dealt with the problem, they might remember the solution. And if they did, sometimes graphs would really move them forward. So lessons learned, solutions to problems are meaningful. They understand why their definition is the way that it is. They know why it's for all epsilon and their existent in instead of the other way around, or why epsilon is greater than 0 instead of greater than or equal to 0. It's persistent in two ways. One way, in the creation of their definition, after they resolved a problem, usually that remains stable throughout other iterations. But there's also things that seem to readily reappear 6 months later. Once they might have been brought into some sort of state of remembrance of, oh yeah, I've seen that graph before. Oh, that graph allowed me to do. Also seen in this one is previously resolved problems can later be non-issues. Non-issues in the creation of one definition, but also in subsequent definitions. And these reinvention activities reinforced and allowed them to reflect on prior work. And you kind of got to see a little bit of the role of the facilitators in this. And we see it as guides on the side, allowing them to engage problems. We also tried to produce conflict, and you saw that with this one with them thinking, oh, well, the Taylor series polynomial is the same as the approximated function over an interval. And so we had to bring in the formula. And we can also be timely solution providers after they've wrestled with the problem for a while. And they're more ready to receive answer. It makes it a little more meaningful. And then lastly, when it showed a series and power series, I feel like graphical understandings that students have can be very pseudo. I think it can be based is something that adds another dimension. Connections between sequences have, and I apologize that apparently I was gone for 5 minutes.
It's the first time that's ever happened. So this is, I just have a last follow-up question. And actually, it's pretty much this question you have up on the screen here. I mean, I can remember myself struggling with understanding power series and Taylor series. And I remember the X being the complicating factor, like not having a good understanding of what the X was versus the N one. And I can remember taking analysis quizzes where I just didn't have a clue. I mean, if I went back and took them now, I'm sure I would have done much better. So what do you think is the solution to, I mean, you had the opportunity to work with these two students one-on-one with almost an infinite time scale in comparison to what we normally get with students. So given that, you have to somehow cover power series in roughly maybe 6 hours of class time total, I mean, for the whole thing, what do you think is the solution to that? I mean, you spent quite a bit of time doing this.
Right, and I've made adjustments in my own teaching, and I in no way claim that there are more important things in calculus than necessarily series and power series. And so I struggle with getting that as well. One of the things that I have been doing is every time I talk about power series, I try to have a picture available. I have activities that they do relative to some sort of graph. We try to address some of these issues that I saw with many.
But then a couple slides ago, you said something about the graphical representation leading to a fuzzier, maybe it was just a fuzzy understanding and not a fuzzier understanding. Pseudo understanding.
Yeah. So the idea is to move this graphical understanding from something that's very pseudo to something that at least reflects some of the formal structure. So I would classify at the beginning Megan and Belinda's graphical understanding of Taylor series was kind of the pseudo understanding that maybe allowed them to get by with producing some correct responses to many problems. But in the end, they were actually viewing the Taylor polynomial as identical to the function that it was supposedly approximating over an entire interval. So that understanding is in error, is inconsistent with formal theory. So lessons learned is that students coming in can have very pseudo understandings. And the idea as a teacher, we want to move them to something a little less pseudo. And so I want to support that movement. Some of the things I've used is Mathematica or something where they can zoom in and see that, oh, even though these two graphs are touching in this window, doesn't mean they're really the same because I can zoom in. So when I say it's important to produce graphs, it's important to do that, but I'll at the same time talk about some of the underlying structure, that even though these things are touching, that's not really what's going on. And I like to highlight a particular point, like x equals 1. And if I can walk away with students understanding what's going on at a point for Taylor series, and if that's the big takeaway from Power and Taylor series, then I think that's a pretty good thing. If they can somehow articulate, well, what's going on at a point, and if they can start connecting, oh, that vertical, okay, so really series are a part of this. It's not just because Power series has the word series in its name. It has the word series in its name because there really are series here going on at particular points.
That makes sense. I like that idea. I wonder if the use of graphing calculators is actually hurting us here, because the pixelation on the calculators is so bad that graphs do look like they are the same endpoints when they're not, and it's difficult to zoom in and out easily and things like that. So I wonder if this is where our calculators, which are supposed to be helping us, might actually be handicapping us.
But it's also an opportunity to have a conversation and say, this is what the calculator is doing. This isn't necessarily what's really going on. And there was a moment where Belinda alluded to our calculator. She actually alluded to a table of values, because you can do the TI-80 whatever, and it will produce a table of values for you. And she alluded to, well, after a certain point, all those numbers start matching up. So that was supporting her conception of these are really identical after 2 or 3 in, because the numbers are matching up. And she would take into account that the calculator is rounding. So had that been caught in class, we could have had a discussion about that. Say, this is what's really going on. And another issue is, I'm sitting here saying, do graphs and have discussions about graphs and have particular discussions about what's going on at x equals 1. Graphs are time consuming. If we're talking about doing this in 2 or 3 class periods, you're not going to be able to do a whole lot and do a lot of graphs. So I try to have pre-made stuff. I may take them through one graph, and on their homework I have them do a graph in a lot of detail, but then I have a lot of some pre-made stuff, because it's time consuming for us as teachers. It's time consuming for the students.
Yeah. All right. Well, I want to thank you for doing the webinar today. I'm sorry about the technical glitch we had in the middle. And I'm not going to bother with the polling because we had so few participants, or with the evaluation. But thanks for hanging out till the end here, Nell. And sorry we went over a little bit, but I figured we better because we lost 5 minutes in there. So thanks, Jason, very much for doing the webinar today. And I will see you guys in the next webinar, maybe.
Okay. Well, thank you very much.